In this video, we're going to look at the power function. Now we're going to spend the first 5 minutes or so just looking at a little bit of the mathematics, and then we'll go on and we'll look at the actual function in the graphical calculator, and then we will write the assembly language code and run it on our CPU. So the power function is of this form here. Y is equal to ax to the power of n. Now the value for a and the value for x for a power function are real numbers, so just every number. The value for n is more specific. It's every number that is greater than or equal to 0. So we could put a value in for n which is less than 0, and we would get a different function out, but it wouldn't be defined as what we call a power function. Now, things are a little bit simpler on our computer because we only have integer values. So we have, for example, -3, -2, -1, 0, 1, 2, 3. So everything we do is actually going to be integer values. So we're going to have an integer value for a, and also for x, and also for n. But again, we have to make sure that the n is greater than or equal to 0. So let's put one example in. If we make a2 and the value for x3 and the value for n2, we're going to have 2 times 3 to the power of 2. So it's going to be 2 times 9, which is 18. So we just want to be able to generate this little function here. It looks quite straightforward. And I've put a note here down below. We can see our values of a can range between all our negative integers and positive integers and the value 0, and also the same for x, but n can only be 0 and positive integers. There is, though, a couple of things that are quite interesting, and it's a nice little one to start off with. Let's say, for example, we were to look at taking the powers of numbers. So if you had 2 to the power of 3, it's equivalent to multiplying 2 together 3 times. So it's 2 times 2 times 2, which gives us a value of 8. Now if we do 2 times 2 to the power of 2, then it's going to be 2 times 2, which is 4. And then we have 2 to the power of 1. So how do we then define 2 to the power of 1? What we're multiplying 2 by? We're not multiplying it by 2 because that's 2 to the power of 2. So we, by definition, say that 2 to the power of 1 is equivalent to 2 times 1, which is equal to 2. So it means that all numbers raised to the power of 1 are going to give us just the number back. So for example, if we had 2 raised to the power of 1, we get 2, 3 raised to the power of 1, we get 3, 4 raised to the power of 1, we get 4, and also 0 raised to the power of 1, we get the value of 0. So we can write down more generally, x to the power of 1 is equal to x. So that's going to be part of our program as well. So we have looked at raising powers of the numbers 3 to 1. What happens if we raise a number to the power of 0? Well, let's look, for example, if we had 2 divided by 2. So 2 goes into 2 one times, and there's no remainder. So 2 divided by 2 is 1. But if we write 2 as 2 to the power of 1, because we know from above that is just the number 2, divided by 2 to the power of 1, then we can write that as 2 to the power of 1 minus 1, which is 2 to the power of 0. So 2 to the power of 0 therefore must be the value 1. So take your time to read over that again to ensure you understand it. So it means that if we were to raise a number to the power of 0, we just get the value of 1. So 3 raised to the power of 0 is going to be 1. 4 raised to the power of 0 is 1. And 5 raised to the power of 0 is 1. So we can write it again more generally. Any number raised to the power of 0 is equal to the value of 1. So these two here, x to the power of 1 is equal to x, and x to the power of 0 is equal to 1, are two things we want to take note of. But there is one complication here, and we'll just mention it briefly. If we had a 0 raised to the power of 0, then what we're going to get here, because this thing here is going to fall apart, because 0 raised to the power of 0, if we look above here, we started off working through this little proof of sorts by looking at dividing two numbers. But if we were to, say, divide 2 by the number 0, and we said that that value gave us a value x, we could rewrite that as 2 times the value, 2 is equal to x times the value of 0, and then ask what values of x will satisfy that equation. But in this instance here, there's no values of x are going to satisfy that equation. There's no number that you can multiply 0 by in order to get the number 2, okay? So really that is a little proof of the division by 0 is undefined. There is no answer. But if we were to look at it the other way, if we had 0 divided by 0 is equal to x, then we could rewrite that as 0 is equal to x times some number 0. And then we could ask, how can we solve this equation here? Well, the solution for this equation is all numbers of x, because 1 times 0 is 0, 2 times 0 is 0, 3 times 0, 4 times 0. Every number that you multiply by 0 gives us a number 0. So differently from the above, where that is undefined, there is no solution. In this example here, there's an infinite number of solutions. So every value of x is a solution. So therefore we say in that instance that the solution is indeterminate. So we can see here then, if we were to start off with 0 divided by 0 and work through this process here to try and work out what 0 raised to the power of 0 is, we're not going to get a defined answer. The answer is going to be indeterminate. But what we do sometimes in mathematics is we pick a more convenient solution that is actually of use under most circumstances. So what we do then in this instance here is we just say 0 to the power of 0 is actually equal to 1. So we do that by definition. But there might be certain situations where mathematics where defining x to the 0 to the power of 0 is equal to 1 is not of a lot of value, okay? But for our purposes here, we're going to stick with what is usually done certainly within the world of computer science, and that is that we're going to define 0 to the power of 0 is equal to a value of 1. Okay, so it means that in summary, our little power function here is going to be y is equal to ax to the n. We'll have to take a note that n is greater than or equal to 0. We also know that x to the power of 1 is equal to x to the power of 0 is equal to 1, and in the special case here, 0 to the power of 0, we're going to make that 1 as well. Now just before we finish here, that's the end of our little bit of mathematics, so we'll go on to some interesting things next. But one thing to note here is that if we wanted to, we could build a circuit up that would run through we'd be able to run through the code, and if we had the 0 raised to the power of 0, we could write a little bit of code that would generate a warning for us. So it would just be a little, it wouldn't be an error, it would be a warning saying we have cropped up with a 0 to the power of 0. We'll continue doing the rest of the code, but we'll just take note of it. Okay, now we could do that, but we won't do that for the moment. For the moment, in this instance here, what we'll do is we will just check that n is actually a number greater than or equal to 0. If n is a negative number, then we will come up with an error, which we will actually call a trap. So we'll come up with this trap, which will then stop the code running, and we will come up with an error code for that trap. But we'll see that working just in a moment. Now let's look at the function on a graphical calculator. Now I'm going to use Desmos, that's D-E-S-M-O-S. You can type that into a browser and it will bring up this graphical calculator online, which is free. So we can type in y is equal to ax raised to the power of n. We can pick the variable a and also the variable n. Now in our computer we have only integer values, so -3, -2, -1, 0, 1, 2, 3. We don't have the values in between. So it means that the value for n we know is going to be a positive number, so it's greater than 0, and we could pick an upper limit of say 10, and it's going to be in steps of 1 because it's only integer values. The value for a can be negative and it can also be positive, but again in our computer it's integer values, so it's steps of 1. Now in this graphical calculator it's going to have the x will be the real number line, so it's going to be every value, so it's going to be a continuous input here along the x-axis. But again in ours we're just going to have the integer values, so if we were to draw this function in our computer we would only have the point here at 1, 1 and 2, 2. We wouldn't have the values in between, so we would just have the points which would generate the function. Now the value for our n is meant to be a value greater than or equal to 0, but we can generate functions whenever n is less than 0, so we'll quickly put that in just to show you these functions. But these are not the power functions, okay? So here are the power functions here, which have been generated. Those are the ones we're interested in. Now if I make n negative, then we get the reciprocal of the power functions, okay? So that's this family of functions here. So we're not interested in this family of functions, okay? So we will put that back to a value of 0, and we can put a as a value of 1. So now if we were to have the a as a value of 1 and n as a value of say 0, so we're going to have x, which is some number raised to the power of 0, okay? So any number, as we said, raised to the power of 0 is just a value of 1. And you can see here it draws this line out, so every number here raised to the power of 0 just gives us a value of 1, and it draws the straight line. Now if we move that up to a value of 1, then we're just going to have the value of x to the power of 1. So any number raised to the power of 1 just gives you that number, okay? So it's going to be 1 raised to the power of 1 gives a value of 1, 2 raised to the power of 1 gives us 2, 3 raised to the power of 1 gives us 3. So we're just going to get the line y equals x, and then we're going to have the line y equals x squared, x cubed, x to the 4th, the 5th, the 6th, so on and so forth. Now the value of a here, it just adjusts the amplitude of the function. If you like, it just stretches the y-axis. So if we stretch the y-axis, it'll make the function look like it's getting squeezed in. So here we can see it here, it just multiplies that function, and you can see the function looks like it's getting squeezed in. So you can see that better if I maybe put it here. You can see that squeezing of the function. Okay, now the other thing the a value does is if the a goes negative, it just mirrors it onto the x-axis, so it flips it on the x-axis. Okay, so that's the basis of our function, and you can see here again if you put in the values 0 raised to the power of 0, in this instance here it defines it as a value of 1, and that's the definition we will use. And any number raised to the power of 0 gives us a value of 1, and any number raised to the power of 1 will give us just that number. Okay, so that's us looked at everything we need to know about the function, and we know what it looks like as well. So let's go ahead and we will write our assembly language code for this function. Now we have our two pieces of code here. The one on the right is the calling function, the one on the left is the subroutine. So let's talk through the calling function first. We have to push our variables onto the stack. So we have the variable a, x and then n pushed onto the stack. We then jump to the subroutine math_power. Now math_power is just a memory location in the ROM. So I've picked a memory location as per our mathematics library and the position of that according to our memory map. So that's the position I've chosen. So at that point there, it jumps to the subroutine. Now I'll talk through the subroutine just in a minute. So let's say it's worked through the subroutine and it's got a result. So it stores the result in a memory location here called result. Now what I've done here, just to make it easy to see what's happening, I've taken the result and I've put it into register R5. So register R5 will always contain the result of our power function, but of course you can place that anywhere. Okay, so now that we've done that there, you can see here that we can choose the actual values for our test function here at this point here. So our start address is 8 × 100. It's just a bit random, it's only just for testing, and we can change the value of our a and our x and our n, and these are passed into our subroutine. So here is our subroutine here, and I'll try my best to talk my way through it to make it as understandable as possible. So whenever we jump into the subroutine, the very last thing that goes on to the stack is the return address. So it means we have to pop the return address off first. So we pop this off and place it in return address. Now the next one that gets popped off will be the index register, then the R0 and then the R1. Okay, so it means that the index register is going to contain the value for our indus, which is n. R0 will contain the x and R1 will contain the a. Now I move a copy of the x again into register R2, and you'll see why I do that just in a moment. So now we continue down to the next part of the program, and now the way I've designed the program is I'm really working with it in terms of the indus. So we know that if the indus is less than 0, then we want to stop the program, because we know that we're not allowed values for the indus less than 0. So I've got this thing here saying jump to trap A. So we come down here and we do this thing jumping to trap A, which I'll talk through. In fact, I'll just talk through just now. So in this position here, we put a number 1 into a memory location in the RAM called trap 1, and then we just return back to this point here after the jump to subroutine, and we load the result into R5 and then we end. So I've actually built a little bit of extra circuitry to deal with these traps or these errors, and I'll show you that as soon as we've walked through this code here. So if the value for n is not less than 0, then I'll look at it in terms of if it is equal to 0, if it's equal to 1, and then all of the rest. So if we look at the indus, if it's equal to 0 here, then we jump to 0. So in that instance here, we jump down to 0. In that case, it puts a value of 1 into register R0. Okay, so R0 was the value for x, but now I'm just replacing that with a value of 1. Because whenever we work out this indus is the power of 0, you can see here that we're going to have x to the power of 0 is equal to 1. So no matter what value for x we have, whenever we raise it to the power of 0, we always get 1. So we can just replace that x with a value of 1. So I do that here, replace it as a value of 1, and then we come down here and we've got our jump at this point here, and it jumps to amplitude. In fact, we don't even need this jump here because it just goes straight down to amplitude, so I could actually miss that out. So we get down to the amplitude here, and at this point here we're going to multiply our x to the power of n, which is just 1, with a constant, okay, and the constant is going to be held in A, which is register R1. So we do that multiplication, and that gives us our result there in that instance, and then we store our result in R0, and then we jump to the return address and we load the result into register R5. Now the other option here is the next one, where the value of our index is a value of 1. So in that case there, we don't bother coming down and changing this R0 to a value of 1, we just leave it as it is, it's just a number. So we're going to have in effect 5 to the power of 1 would be 5, or 6 to the power of 1 would be 6, 7 to the power of 1 would be 7. The number just gets left as it is. So that gets head down here, and we just come down here. Now we've got the correct numbers in R1 and R0. We can do the multiplication with the x to the power of n with the value of A again, and we work through this here, and then it jumps back up to the return. Now finally, the other option is that the index isn't 0 or 1, it's a different value, in which case we have to go through a little multiplication loop. So if we come down here and it's not a 0, it's not a 1, then it must be 2 or greater, in which case we are going to multiply the value in register R2 with R0, and this is the reason why I put this move R0 and R2 into R2. I needed a copy into R2 so we could do the multiplication. So this works through the multiplication, R2 and R0. It then decrements the index, index register, which contains the index, and we jump if it's equal to 1 to amplitude, because then it would have worked through all of the multiplications, and again when it gets to the amplitude it will multiply it by that constant value A again and then finish. Okay, now if it doesn't equal 1, then it just jumps back to this line power here, and it just works through the next multiplication, and it keeps doing that, and it keeps multiplying out until it's all finished, and the jump of equal is the if the index register is equal to the value of 1, and it jumps to the amplitude, multiplies out the amplitude, and then finishes up here again in the jump to subroutine, and it loads the result in register R5. So that's how it works. I'll show you it working quickly just now, but I had to work through maybe about 15-16 different combinations just to test them all, make sure they are all actually doing what they're meant to do. And the strange thing is it doesn't take that long to write the code, but it takes a little bit longer to actually work out test routines to test everything to make sure you get results in all circumstances. So let's have a look at this actually running. So we will look at two examples here. The first one is 5 times 10 to the power of 3. So that's 5 times 1000, so that's 5000. And the answer should be 1388 in hex, which will go into R5. So we'll watch that running. So that's it running through here. It only takes a few seconds. And you see the answer 1388. So in the second example, I have set the index to a negative value. So let's look and see what happens when we run through this. Now you'll note that I've got this extra section here built in, and it's called trap. So in effect this is used for us to detect any errors in our code. So in this example, we know we're not allowed to have the value of n less than 0. I've deliberately put that value in for this example. Now I'll stop this running, and you can see that if we look quickly at the code, whenever we have that negative value for the index, it jumps down to trap A, it puts a value of 1, in a special address. Now that special address is called the trap address, and it's actually set up here, and I've picked E7F0 within the RAM, so it's just one single memory location, and I can put any value into that memory location from 0000 to FFFF, so we've got 65,000 or so values that we can use. Now if you have the look at the circuitry, I've adjusted the memory address register just slightly. So we'll go in here quickly to have a look and see. So the memory address register used to just receive, we would pulse a value to it, a 16-bit value, and then we would set that in the memory address register, telling us that we're going to go to a particular memory location. So if we have a little circuit here and we set it up and we test to see whether we're actually going to this trap address. So if we're going to the trap address, then we're going to go to E7F0. So if I was to put that E7F0 in here, so we're going to have the F here, we're going to have a value of E here, and we're going to have the value of E is going to be here. So at this point here, we know we're going to pulse that particular memory location. Okay, so this point line here goes high. So whenever that is set within the memory address register, then this line here goes high here, and the trap value comes on. So when this trap light comes on, I've got this at the top level saying, hold on a minute, there's a problem. Okay, so the little trap light comes on. But now, not only do we want to know if that there's a problem, we want to know what the problem is. So we want to be able to get this number 1 coming out. So the number 1 is going to come out whenever the control has actually been set. That is, we're trying to write the next value into the memory location. So if this was to go low, we would wait until the next value came along. So let's say the next value is our value of 1, which is our trap error code. Then whenever this here is set, it sets that value in the register, and then whenever the next enable comes through, it enables that value 1 onto the bus, and that gets taken up to the top level as the trap. So that means we've got a method here of having 65,000 or 2 to the power of 16 different trap values, and we can use these in order to ensure if we have an error in the code, then we can check and find out what that error is. So quite a lot involved in this video, but we've come quite far. Now I suggest that you download the stuff in the resources section and test these out for yourself and go through one bit of code at a time and just work through this extension onto the memory address register. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.